In this video, I'm going to show you the complete design and drawing of the Waffle slab in Etabs. The given situation is presented. You are given with the FC prime of concrete as 5 ksi, F560 ksi. The floor height is 10 feet. Columns are 36 by 36 inches. The center to center span of the slab is 33 feet. Live load is 100 psf. Super dead load for finishes is 40 psf. We have to calculate the thickness of the slab and drop panel dimensions, rib dimensions and spacings, and we have to design the reinforcement and detail the slab using the code ACI 318. So the first step will be calculating the slab thickness or the waffle thickness. Since we are considering without drop panels for conservative design, let's start with the exterior panel thickness calculation. The panel thickness is of clear span, so 33 into 12 minus 36 is the column dimension. Gives us 12 inches thick waffle slab for exterior condition. For interior condition, we will have to divide by 33, which gives us 10.9 inches. We enhance the slab thickness by 40% as waffles are hollow compared to solid slab section. So slab plus waffle is approximately 17 inches required in our case. The waffle slab is usually 3 inch to 5 inch. So the slab part is taken as assumed as 3 inches. The depth of waffle is the remainder of the rest. Let's take it as 3 inch minus 17, that gives us 14 inches. So assuming the width of the waffles as 6 inch, waffle's center to center span is 2 feet. We may revise the assumptions if the slab fails in shear and flexure in the later part of the video, which we will check for. So the drop panel dimensions are calculated based on the center to center span. The center to center span in both directions is same here, so the dimensions will be similar. It is 1/3 of the larger dimension in both directions. Thickness of the drop panel is equal to the waffle depth, but it should not be less than the slab thickness divided by 4. So we are taking here as equal to the thickness of the waffles, that is 14 inches, which we calculated previously. So now starting with the Etabs software. Defining the grids, and the number of story is 1. The story height is 10 feet. We may directly select waffle slab from here, but in order to understand the design procedure in detail, we may start from scratch. After defining the grids, we may close the 3D window so that we get a clearer view. So first we will define the material properties. The material for concrete was given as 5 ksi or 5000 psi. You may check the property modify show strength parameters. Okay. Now add the rebar material. Let's name it as G60 deformed. Now in the next step we will define the column section. The column was 36 inch by 36 inch. The property modifiers according to ACI 31808 are 0.7 for gross moment of inertia to incorporate the cracking. Now use the rebar which we defined, rebar material. We may delete the unwanted extra properties excluding the one which we defined. So now here we are left with the property which we defined. Now we will define the slab or the waffle sections. We need to add a new property. Let's call this as waffle. Select the material. Now, in order to understand the difference between shell thin and membrane, you need to go to the video whose link is given in the description. Right now, I'm assuming we have gone through it. So we are taking as shell thin. Now select the type as waffle. The overall depth was 17 inches including the slab as well as the waffle. The slab thickness which we kept is 3 inches as a trial iteration. The waffle width is 6 inch and the center to center spacing is 2 feet, that is 24 inches. Now the slab property modifiers according to ACI code is 0.25 of the gross moment of inertia. That is 25%. Now okay. Now we need to define the drop panel properties here. The drop panel thickness is equal to the ribs thickness. But since we will replace the slab with drop panel section, so the drop panel will include slab's thickness as well, which makes it 17 inches. As we have to replace that region in Etabs. Basically it's drop panel plus slab thickness here. Now we need to go to the load patterns. Dead and live load have already been defined here. So we need to add the superimposed dead load which we were given as 40 psf. So now we will require to model the structure. Since there are no beams, so we may model the columns in the next step. Pick column. The columns are at a distance of 33 feet center to center as given in the condition. Make sure that the columns are properly joined with the slab. If it's not so, then press Ctrl and Z to undo the operation and redraw. Now in order for modeling purposes, we may select a non-frame section, and since the drop panel dimension was 11 feet, So half of 11 feet is 5.5 feet on both sides of the column, and in inches it will be 66 inches. So we mark the cross lines having the property of none, since we don't want stiffness of the beam to be incorporated here. Later on we will delete this none beams, which is only for the modeling of the drop panels. Now select the slab and the beams modeled for the purpose of drawing drop panels. Go to edit and divide the shells. Cookie cut the floor and extend the floor frames. So now we will see the slab has been broken from those lines. Now select the property of the beams which you defined and press the delete button. Delete the portion of the slab where drop panel need to be modeled. Now we need to draw the drop panel in the cavities. We have to be careful while drawing the slab. If the slab overlaps with another slab, then Etabs will create a problem, and it may sometimes give you an error as well. It's not necessary that we require meshing in this slab by manual means. The automatic meshing option has already been selected from inside the analysis options, as seen in the previous videos how to apply auto meshing option. So we may continue further here. Now in order to depict the slab and the drop panel by means of color, I may show the object properties by the colors. So you see the waffle slab plus the drop panels is modeled here. Now click on the check model to see if the slab is overlapping and select the least tolerance for highest accuracy. Click on joint objects and shell overlaps and then go to OK. The model has been checked, no warning messages. Now it is ready to run, but before that we need to assign the diaphragm and the loads. Assign the rigid diaphragm since concrete, so it's already rigid defined. Apply and OK. Now you see the stiffness of the slab has been distributed all over the columns. It is basically important in case of earthquake loading. For the design of slab, usually we don't consider earthquake loading since it's governed by gravity, as the stiffness of slab is high in earthquake loading case. So making the column support fixed as bottom. Now turning off the other objects and selecting the shell elements so that we can assign the uniform load. The live load was 100 psf. Select again and this time assign the super dead load. that was 40 psf. Now in order to rectify, right click on a slab panel and you can see the list of assigned loads. Now before running the model for analysis purpose, you may check the cover of the slab which you want to incorporate in the design. The most important thing to check is that you select the appropriate design code, that is ACH 1814 here. Now go to load combinations and the default load combinations will be on the basis of the code you selected. Now for a serviceability check, add a long-term deflection load combination which has no purpose in design but to check the serviceability of the slab, whether the selected 3-inch thickness was sufficient or not. So the lab load is considered as 1.5 times and the dead load as 3 times for creep and shrinkage and the permanent load deflection contribution. Now in the design options, we need to import the combinations other than long-term deflection, which is just provided to check the deflection whether it is in the limits or not. Now run the analysis. So you see slab is automatically meshed as the auto meshing option is on by default. Now check the long-term deflection and draw contours in the direction of gravity. So for long-term deflection limit, we have used ACI 318 table and the deflection limit is span divided by 240. So in our case it becomes as 1.65 inches. The deflection So you see in the bottom left corner of the screen, the maximum deflection is in absolute terms is 3.87 inches, which exceeds the limit for the deflection. Sometimes there are errors in analysis, so you may check this again before revising the cross section. Click on undeformed shape and then go to the deformed shape once again. Select the same parameters after rectification whether you selected the appropriate parameters or not. UZ is in direction of gravity. So the deflection is unchanged, which is exceeding the limit of 1.65 inches. So we need to increase the slab thickness, that was 3 inches from the 17 waffle thickness. Go to waffle. Now the revised slab dimension from 3 inches to 5 inches. The depth of waffle remainder is 12 inches. If the slab fails again, provide camber. The depth of drop panel is also revised to 12 inches, equal to the ribs depth. But we may not change in the drop panel properties because the overall summation of slab thickness and drop panel is still 17 inches. And in drop panel properties, we Now after that, run the analysis and check the long-term deflection limit once again. On the combination of long-term deflection. So the deflection is still exceeding the limit. So we will provide the camber in the drawings. When we will detail in AutoCAD, we will write that provide camber whatever is above the limit. Usually the deflection, if exceeds the limit, then we provide a camber whose limit is not greater than the twice of the deflection limit itself. Unlock the model. Since here is the deflection exceeding the limit, so we will provide camber in these selected regions. So let's ignore the deflection exceeding the limit for here, as we are able to provide a camber of approximately 2 inches, which we will later calculate accurately in this video. Deflection limit is still exceeding after running the model again and again, but we cannot exceed the limit of 17 inches slab thick and waffle thickness due to architectural purpose. We are restricted there. So the last option is providing camber. Now we will calculate the strip width before designing the slab. Since the design steps are using direct design method, so the column strip and the middle strip is important to be drawn. Column strip width is quarter of the clear span in shorter direction. Here both spans are of 33 feet. So the width of column strip is quarter of 33 feet, that is 8.25 feet or 99 inch. And the width of the middle strip is the remainder of the span left after the column strip. So drawing the design strips for A layer, you may check the strip width option so that you may see the width of the strip. We need to turn on the midpoint snap for drawing the middle strip. Then apply and close. Now you see a midpoint triangle snap appears, which helps in accurate and easy drawing and picking up of the joints. So now we are done with drawing the strips in layer A. For layer B, starting with the column strip, if you mistakenly draw the wrong column strip, press undo by using Ctrl and Z. Now draw the middle strip similar to that in layer A. Now we need to assign the rebar material to the strips. Let's turn off the other layers. Press escape so that strip drawing is over. Now go to design overrides for the slab. Select the steel material on which area of steel or number of bars will be calculated. Similarly for the middle strip of layer A. Click on OK. Now turn on the layer B. Similarly for the middle strip of layer B. Okay. Now set the default viewing options. Now run the analysis. Start design of the concrete slab. Display punching shear check. The slab passes in the punching shear except the edge condition. So now we need to use the Excel sheet for the edge conditions. So the Excel sheet is now open. We need to input the parameters. That is the slab thickness is 17. Effective depth of slab is 387.5. And the slab thickness is 17 inches. That makes it 425 mm. The column dimension is 36 by 36. That makes it 900 mm. Yield strength of steel, okay. (5000 psi multiplied by 0.0069). So it gives you approximate strength of 35 megapascals. For the force, we need to go here in Etabs. The shear force is in kips, so we need to convert the units into SI and go back in the menu. It is 346.6 kilonewtons. The moments in direction 1 and 2 are 167.5 and in other direction same. The parameters are defined. Now we need to check whether shear reinforcement is required or not. Punching shear reinforcement is not required. So you see Etabs sometimes give errors as it was exceeding the factor or the limit of 1.